Kriging? Kriging, a spatial prediction methodology based on spatial interpolation, was first developed by Mathern based on the work of Kriging to predict oil reserves. Kriging has been applied widely in air quality analysis, geology, hydrology, ecology, etc. The major application of this technique is to predict values at unmeasured locations while assessing the errors of these predictions. It relies on the notion that unobserved factors are autocorrelated over space, and the levels of autocorrelation decreases with distance. A trend estimate, μ, s, is determined, which can be defined as where zs is the variable of interest and s indicates the location of the site I. It is composed of a deterministic trend μis and a random error term epsilon I, s. The random errors are autocorrelated over space. The expected value of z's results in different types of Kriging, namely simple, ordinary, universal, intrinsic Kriging, and so on. However, universal Kriging is preferred to other Kriging methods as the trends depend on explanatory variables and, unknown, regression coefficients. The correlation between z's and zs plus h, does not depend on actual locations, but only distance h between the two sites. This is possible by assuming weak stationarity in all three cases. This indicates a constant variance of 2 gamma, h, for any s and h, where gamma, h, can be expressed as where var is the variance between s and s plus h. When 2 gamma, h, is plotted versus distance, the plot is called a semivariagram. A semivariagram depicts the spatial autocorrelation of the measured sample points. One of the major steps is to select an appropriate semivariagram model that best fits the relationship between gamma and h. There are 3 models that best explain the relationship, i.e., exponential, spherical, and Gaussian. In this lecture, only spherical model is presented, and the specifications are: the different models, spherical, exponential, and Gaussian, rely on parameters that describe their shape and level of spatial autocorrelation in the data. C0 in the above equation is called the Nugget Effect and reflects discontinuity in the variogram origin as caused by factors such as sampling error and short-scale variability. The origin of the term nugget originates from gold deposits, as gold commonly occurs as nuggets of pure metal that are much smaller than the size of a sample. It can result in strong variability in the sample when physically close, and therefore discontinuity of the variogram at the origin can be observed. The rate of variogram reflects the degree of dissimilarity of more distant samples. At large distances, a variogram can increase indefinitely if the variability of the phenomenon has no limit. However, if the variogram stabilizes at a value, called the sill, it indicates that beyond a certain distance z's and zs plus h are uncorrelated. This distance is called the range, denoted by a. It determines the threshold distance at which gamma, h, stabilizes. C0 plus C1 is the maximum gamma, h, value, called sill, and C1 is referred to as partial sill. Figure 1 illustrates a semivariagram. Illustration of a semivariagram.